Okay, we're continuing with Chapter 17 Plus. This topic's so great, it has two different titles. Just two different ways of saying the same thing here, composite functions or composition of functions. But basically what's happening is we're going to take two functions and combine them, not through addition, subtraction, multiplication, division, etc., but by putting one function into another. That's what we refer to when we speak of composite functions or compositions of functions. As we go through this video, we're going to cover four basic things here. We're going to talk about what the notation is so we can recognize a composition when we see it. We'll just look at some pretty easy examples. Then we're going to work backwards. So when we have a function that's already is a composition of two other ones, we're going to be able to tell what the original functions were. And then we're going to connect this back to domain, which we've spoken about previously. All right, so first of all, the notation. Just like we have two titles, we have two different notations for it. So what you see on the left and the right here, they mean the exact same thing. So we have a function, right? So we have like f of x. And we know that if I write, say, f of 2, that means I'm putting the 2 into the function where the x used to be. Or if I have f of 3x, then I'm putting a 3x into the function where the x used to be. That would be a function transformation in that second case. That would be a horizontal shrinking. It would be 1/3 as wide, a horizontal compression. A function composition literally takes a function and puts it into another function. So we had f of x, and instead of x, we're putting in a whole other function, g of x. And if that makes sense already, great. If it doesn't, just wait until we see the next screen. But I just want to point out on the notation, on the left, I like the notation better because it's a little more obvious that g of x is the inside function. We are putting g of x into f of x, not the other way around. The notation on the right means the exact same thing. This was just developed by a different human being at a different point in time, at a different place than the other notation, and they had enough cool mathematician friends that, both of these notations stuck around. So the notation on the right says we're going to do g of x first, and then, that's what this circle means. It means do the thing to the right of it, and then do the thing to the left of it, which is g. So we're going to do g of x, and then apply f to that. All right? And the circle, I made a point of this in the last video, the circle is not a dot. If I had f dot g of x, that means f times g of x. If I have f circle g of x, that means f of g of x. Okay, enough of this. Let's look at some examples. So here we've got two functions, f of x and g of x. So we're going to simplify. First, f of g. That means we're going to put this entire function here into where that x is. Okay, so it becomes f of x squared plus 4, which becomes 3 times x squared plus 4 plus 2, and then we distribute and simplify. Great, that's our final answer. In the second example, we're going to do g of f of x. So now we're going to take f and put it into that x. So it's g of 3x plus 2, which is 3x plus 2 squared plus 4. And then we expand and combine like terms. And we get an answer. And the one on the right, whatever, we can compose a function with itself. We can do f of x. Same idea. We're going to take f of x and put it into f of x. So this is f of 3x plus 2, which is 3 times 3x plus 2 plus 2. And then we distribute and we combine like terms, and we get an answer. I want to point out that f of g and g of f were not the same thing. All right? Generally, that will be true. F of g of x is not generally equal to g of f of x. You should always assume that they're not equal to each other. But could it possibly be true? Yeah, there are special cases where they're going to be equal to each other. In the boring case where f of x and g of x happen to be the exact same function, then of course their compositions will be equal regardless of the order. But to give you just a really simple example, here, those two are going to be the same no matter what order we do them in. But again, that's a special case. We should never assume that they're going to be equal. So now let's look at working backwards. So decomposing a composition of functions. So right now, it might not seem like it has too much of a purpose other than here's a thing that we can do. I mean, look, you might not feel that anything we do in this course has a purpose. And it's a fair criticism. I understand where you're coming from. But for those of you who are really into the math just because it's fun, I assure you that being able to identify the quote-unquote inside and outside functions is going to be very, very important later on in future math classes. So I want to practice that now. So here we've got square root of 2x plus 1. So we want to invent functions g and f so that when we compose them in the correct order, we get the square root of 2x plus 1. And we just need to think about what's inside and what's outside. When I see this function, I see the outside as being the square root of some stuff. You know, we could put the 2x plus 1 in parentheses, and parentheses might be the key to all this. If you either see parentheses or if you could write parentheses, that's going to indicate that you've got something inside of them and then something outside of them. So in this case, my outside function is going to be the square root of x, and then my inside function will be 2x plus 1. And we can see now that when I put 2x plus 1 in here for the x, I get the square root of 2x plus 1. Second example, this one comes with parentheses in it already. We have parentheses, some stuff raised to the power of 4. So my outside function is going to be x to the power of 4, and then my inside function will be whatever we saw inside. And again, when I put 4 minus x in for that x, I get 4 minus x, all raised to the power of 4. You know what? We should do one with a fraction also, because this is one that doesn't have parentheses in it, at least not immediately at first. But we know that 3 is being divided by this entire thing. So that means that our outside function could be considered to be 3 over x. And our inside function could be x plus 1. Again, I put x plus 1 in for that x, and I get 3 over x plus 1. This could take a little getting used to try to really think about what's inside and what's outside, but there's not a lot of steps to it. There's nothing you need to write down. You just need to look at it and kind of be able to see it. And you know, there's also not always one correct answer to something like this. In this case, for example, perhaps we identify the outside function b as simply being the square root of x over 7. In this case, the inside function would have to be 4x minus 2. Or maybe the outside function is just x over 7, and the inside function is actually the square root of 4x minus 2. The composition b of a of x is going to be the same thing in either case. So there's not necessarily a right or a wrong way to do the decomposition. I mean, heck, this thing could have actually been 3 functions, c of b of a of x, and then we just would have put 4x minus 2 into the square root of x, and then we put that into here with the x over 7, and there we have got a composition of 3 functions. So there's lots of ways that you can imagine decompositions. The main idea is that you can figure out at least some inside and some outside. So you can look at and understand the structure of what's going on in a composition. And that brings us to the last thing, which is the domain of a composition. All right, so the first thing we want to think about when we're dealing with domains of compositions is, you know, hold on, let's just figure out the domain of each individual function. So we can look at these, and we should be able to identify pretty quickly that f of x has a domain of all real numbers except for 1, because I'll be dividing by 0 there, and g of x will be all real numbers except for 2/3. And at least some of that information is about to be very, very important to us. So now we're going to do our composition f of g of x, which means that g is going into f. So let's do that. Here we've got, remember, f is 5 over x minus 1. This one's exciting because we're putting a fraction into a fraction. So we have 5 over 4 over 3x minus 2 minus 1. Now we want to clean that up a little bit. So I'm going to change this 1 into a 3x minus 2 over 3x minus 2 so that we can combine those two in the denominator. When we do that, we're going to have 4 minus negative 2, which is going to give us a positive 6, but then also minus 3x. Then I have 5 divided by this fraction, which means we're going to multiply by its reciprocal. And then rather than distribute the 5, what I'm actually going to do is factor out a 3 from the bottom, just so that I have everything as factored as possible. And then this will tell me the excluded value from the domain of my composition clearly has to be 2. Now we're not done yet, and before I move on, I know I didn't talk about this yet, but I just want to point out there's a second way that we could have arrived at x not equal to 2, and that's from the very, very beginning step. Here, we know that we can't divide by 0. We're only going to be dividing by 0 if this fraction itself is equal to 1, so we can just solve that essentially. And that's still going to get us x can't equal 2 in the end. So my domain for the composition clearly is x is not equal to 2. But I got to consider something else, because in the very first step, back here, we have a fraction. And that fraction is 4 over 3x minus 2. And that fraction doesn't exist if x is equal to 2/3. So when we calculate a domain of a composition, we need to consider two things. We need to consider what we get at the very end when we've done all of our simplifying, but we also need to consider the domain of the inside function. You do not need to worry about the domain of the outside function. I can put in x equals 1 here, no problem. The entire thing will still give me a real number out. But I cannot put in x equals 2/3 into this initial step, even though it seems in the last step like I could. Okay, so we're considering two things for the domain. It's the domain that we get at the very, very end, but also the domain of the inside function. Okay, that's it for compositions of functions for right now. We're going to see that this is an idea that we can work in with all the other stuff we've been dealing with so far. It by itself, I don't think it's that tough. It's just a little new notation, another new idea, and it just builds on everything else that we've been learning. And in the next video, which will be the final video for Chapter 17 plus, we'll be dealing with compositions of functions there, doing a little bit more with them, wrapped up with this new topic, which is called inverses of functions, but you're going to have to wait for the next video to learn about that.